Many thanks to this viewer for submitting this problem here for us to work on together today. We have a triangle ABC, H its orthocenter, and M the midpoint of side BC. We have the internal angle bisector of BAC, which intersects the line BC and the circumcircle of ABC at points D and E respectively. We let K be the foot of perpendicular from H to AM, and S is the intersection of the circumcircles of ABC and DEM. We want to prove that the 4 points A, S, D, K are concyclic. I was doing this problem, the first thing that I noticed was that DME is a right angle, and so DSE is also a right angle, and this circle, the circumcircle of DEM, is actually just a circle with diameter DE. And this actually looks really similar to a configuration in another problem that I share on this channel, which I'll link up there. And this other problem, there was a secant to AE intersecting at D, and then we also have a circle with diameter DE. So I encourage you to go check it out after this video if you'd like. Okay, so back to solving the problem, we want to prove that the points A, S, D, K are concyclic. And most of the time with concyclicity, the only thing you can really do is to do angle chasing, which is just to prove, for example, that the opposite angles add up to 180 degrees, which is actually what we are going to do in this problem here. Well, let's take a look at angle ASD. So if we were to do the opposite angles, then we just have to prove that angle ASD plus angle AKD is equal to 180 degrees. And ASD is actually just angle ASE minus angle DSE. Angle ASE minus angle DSE, and we already concluded that angle DSE is just 90 degrees, and ASE, well, since E is the midpoint of arc BC because it lies on the angle bisector, we can calculate what the angle is, but just for a bit nicer visualization, let me construct this point up here. Let me call it, what should I call it? R. Let's call it R. And so this is the midpoint of the major arc BC, which contains A. And so the angle, the arc subtended by AE, for example ASE, we can draw out to AB, and then the angle would just be angle B plus this, which is A over 2. So this is B plus A over 2 minus 90 degrees. And we want to prove that AKD is supplementary to that angle. Okay, and how do we do that? Well, to prove that AKD is supplementary to that angle, we know that AKD is supplementary to the angle MKD. So maybe we can just look at angle MKD, and we just want to show that angle MKD is equal to this quantity. Okay, so let's try to write our thinking process down a bit. Angle MKD, we want to show that angle MKD is equal to B plus A over 2 minus 90 degrees. But what's interesting about this is that we can actually write this in another way, because we know that A over 2 plus B over 2 plus C over 2 is 90 degrees. So we can write 90 degrees as this, and then this would actually just simplify down to B over 2 minus C over 2, which in my opinion is a nicer expression for us to visualize here. And I also made this substitution when I was doing the problem for the reason that if we look at the arc AR, what is this angle? Well, this is actually B minus C over 2. Well, first of all, I'm assuming that B is a bigger angle without loss of generality. And so we know that this is actually like halfway, and this is angle C. So this is halfway minus angle C, which is B minus C over 2. So what's interesting about that is, for example, if I were to look at any angle that's subtended by the arc AR, then this will be B minus C over 2, and we just have to show that MKD is actually equal to that. Okay, but still, MKD is kind of a weird angle. We know that this is a perpendicular drop from H to AM, but that is just a bit weird. So how can we think of this? What can we do with this? And so what I was thinking was that we just have a floating orthocenter here, and that's kind of annoying to deal with. And so maybe we can perform a transformation to make that orthocenter a little bit more useful. And with orthocenters, one of the most important properties is that if we reflect it over one of the sides, like for example BC, then if we reflect it over, it will go to this point, which is actually on the circumcircle of ABC. Well, so why not employ that idea? So let's say I reflect H over this, then all these should be perpendicular. And then let's call this new point H prime. It's a reflection. And how about let's just reflect everything over BC? Well, M still stays on BC and D also still stays on BC, but what is K now? Now K is, as we defined it, the perpendicular, the foot of perpendicular from H to AM. And so now K prime will be the foot of perpendicular from H prime to the image of AM. The image of AM should just be a symmetrical line that looks something like that. And so if we drop a perpendicular from H down here, we know that this is actually K prime. Okay, so why is this helpful? Well, first of all, we can take a look at what this angle is, or what this point is. And let me call it A1. I was gonna call it A prime, but that would be a bit confusing, so let's call it A1. And so this line, A1M, is what AM, the line AM, is reflected over BC. And so we know A1 is actually just the symmetric point of A. For example, if we reflect it over the perpendicular bisector of BC, we will end up with A1. And what's cool about that is, since H is what we get after we drop a perpendicular from A all the way down here, and A1 is over there, first of all, we know that this is a right angle, and so H prime A1 are actually opposite points on the circle. And so H prime K prime A1 equals 90 degrees implies that K prime lies on this circle. It doesn't look quite like it the way I drew it, but, well, it does lie on the circle. Our math shows it. And now the angle we're trying to find is actually just the angle MK prime D. So we can write this as MK prime D. And we also know that K prime lies on this circle, which is quite helpful. But there's something a bit interesting here, which is, for example, if I were to connect the points E, M, R, well, they're collinear because they're all in the middle point. And we've concluded that AR is actually the arc. The arc AR is actually subtending the angle B minus C over 2. And so, for example, AER is B minus C over 2. DEM is B minus C over 2. And so DSM is actually also B minus C over 2. And the reason I said this was interesting is that we want to prove that MK prime D is equal to DSM, or MSD. If I read it like that, it will probably be a bit more apparent to you guys. We want to prove that this angle is equal to angle MSD, and recall that K prime is over here, which also should lie on the circumcircle. And so we're wondering that maybe K prime is just S, because actually, in fact, it has to be S, right? Because we know that K prime lies on this circle, and K prime also lies on the circle DMES because MK prime D is B minus C over 2. That means that K prime has to be one of the intersections of these two circles, which are S and E, and K prime is obviously not E, so K prime has to be S. And our problem just reduces down to proving that K prime is S, or that S is a reflection of K over the line BC. Okay, and how can we do that then? So, because we've concluded that K prime is on this circle and it's on the line A1M, then it must mean that we have to prove that A1, M, S are collinear. So we have now reduced the problem down to showing that the points A1, M, and S are collinear. There are probably multiple ways you can do the angle chasing, but I think the most intuitive and straightforward way is to use a method of false positioning. And I'll show what that means. For example, if we define S prime as the intersection between the lines A1M and the circumcircle of ABC, all we have to do is to show that S lies on the circumcircle of DME. And that also just means we want to show that angle MSE is equal to angle MDE, which if we do a bit of angle chasing, it's this angle, which should be A over 2 plus C. So we want to show that this angle is A over 2 plus C. Okay, but we know that A1MS are collinear, so we can transfer this angle by the collinear points into the angle A1SE. But A1SE is just A over 2 plus C. If you don't believe me, for example, we can reflect. A1SE is this arc, we can reflect it over, we get AE, and then for example, if we were to compute AE, let's do angle ACE, then this is angle C and this is angle A over 2. So we have shown that the 3 points are actually collinear, or actually that S prime lies on this circle, and hence the 3 points are collinear by false positioning. And that is the end of the problem. So the takeaways here, well, to prove that something is cyclic or concyclic, we essentially just have to do angle chasing with the angles of the 4 points. For example, this time we proved that the opposite angles add up to 180 degrees. So there's not that much special things about that. But I think the coolest thing here was the reflection we did here to utilize the condition of H, because H is just a floating orthocenter and we can't really do much about it until we reflect it over to H prime, which lies on the circle, and we have handled the condition of H, and we've also made use of the information with K so we can actually do something useful. For example, that K prime lies on the circumcircle.